All right, so second 4 is basically about taking an equation that has trig in it and not necessarily being able to get rid of the trig, but simplify the trig. Okay? So if you had a problem like this, there's a way that we can simplify that so it's not as complicated. You get 2 different trig functions and you're being divided. In calculus, we might have to do something with this expression. Okay, maybe we have to integrate it or differentiate it. It's going to be a lot easier to work with that if we can simplify it first before we start doing calculus with it. So that's what we're going to look at. So remember what an identity is. It's a formula that is true all of the time. Okay, so it's a formula that's true all of the time, like Pythagorean theorem. Okay? It's not like Pythagorean theorem only works for some numbers. It works for any numbers, as long as you're dealing with the right triangle. Now, there's 3 different categories of identities that we have. We have the reciprocal, the tangent and cotangent, and I know we've written down those before. But we also have the Pythagorean identities, which we have not written down. So I'm going to put the identities back up on the board, just as a reminder of what they are. And the Pythagorean ones I want to talk a little bit about, because I don't think I have not shown you those. So you should not be familiar with the Pythagorean identities. Okay. Right, so here's the different identities that I mentioned up above. The first ones are the reciprocal ones. We use these all the time. If you want to type in cosecant on the calculator, you have to type it in as 1 divided by the sine. If you want to type in the secant, 1 over cosine, and the cotangent, 1 over the tangent. So those we use a lot. The other identities that we talked about before are the quotient identities. If you take tangent, you can rewrite it as sine divided by cosine. And that should kind of connect in with the unit circle. If you remember, on the unit circle, sine was y, cosine was x, tangent was y over x. Well, y is sine, x is cosine. So tangent is sine over cosine. And the cotangent is the reciprocal, cosine over sine. Yeah.
If I wanted to graph cotangent and I was typing in cosine, would I have to put cosine x and then also sine of x? Do I have to put x in both of them?
Yeah. Yeah. Now, the last group of identities are called the Pythagorean identities. Okay, we haven't looked at these a lot yet, so let's see what they are. So the 3 Pythagorean identities are sine squared plus cosine squared equals 1. 1 plus tangent squared equals secant squared. And 1 plus cotangent squared equals cosecant squared. If you know the first one, you can kind of figure out the other 2, but it helps to have those 3 memorized. So let me show you an example. Let's pick a number for x. So x is an angle. Somebody give me an angle.
37 degrees.
37 degrees. All right, so you said degrees, so I got to change to degrees. If I type in the sine of 37 and square it, and I type in the cosine of 37 and I square it, and I add those 2 things together, I will always get 1. It wouldn't have mattered what angle you told me. Because it's an identity. Identity means it works for any angle you want to plug in. So this is a really nice identity, because when you end up with sine squared plus cosine squared in a problem, it all simplifies to 1. So you get a lot of things that disappear and cancel out. So for everything that we're going to do, those are the identities that you need to know. Okay, the reciprocal, the quotient, and the Pythagorean. There's a lot more. Okay, a lot more identities. But for 7.4, that's all you need. So any questions on these identities? Yes?
For the first identity, how does that work out to 1 sine squared plus cosine squared?
Like proving
Yeah.
that that's true. I can prove it. I'm going to hold off on doing that right now, just because it's a great question, but it's just not something you need to know how to prove for tomorrow. And I want to make sure we can get to everything that's going to be on tomorrow's test. But I can definitely show you how to do that. Now, what you can do with these identities is you can rearrange them. So if sine squared plus cosine squared equals 1, you could also say cosine squared equals 1 minus sine squared. You're just bringing something to the other side. You could also say sine squared equals 1 minus cosine squared. So we do have to look for rearrangements of identities sometimes. You cannot use these with other powers. The Pythagorean identities only work with exponents of 2. So you can't change them to exponents of 3. But the other identities, like, let's take this one. Cosecant is 1 over sine. Cosecant is 1 over sine. Well, cosecant squared would mean cosecant times another cosecant. That's cosecant squared. Well, up above it says cosecant is 1 over sine. And you have another cosecant, which is another 1 over sine.
So it would be 1 over sine x times sine x, which would be 1 over sine squared x.
Yep. So if you want cosecant squared, it is 1 over sine squared. If you want cosecant cubed, it would be 1 over sine cubed. So that one you can use with higher powers. These two. Not the Pythagorean. All right, so let's see what we're going to do. So I kind of pointed out the reason why we do it. So the goal is to take something that's somewhat complicated in trig and make the expression simpler to work. Okay, there's a few different tricks that we use to do it. One of the main tricks is to change everything to sine and cosine. So if you have a problem that has other trig functions in it, get rid of those functions and make everything sine and cosine. I'm not going to say that's the way you do every single problem, but a good amount of problems can be done that way. Now, the other thing with identities is there are lots of ways to do them. So usually with an identity, the goal is to simplify it. You might do it in like 4 steps. Somebody else might do it in 10 steps. Different ways to get the same answer. All right. So let's try this. It says cotangent divided by cosecant. And my hint is change everything to sines and cosines. The argument that you use for the trig function, you can call it x, t, theta. That doesn't matter. So what is cotangent? How can I rewrite that? Yep, Kate.
Cosine of x over sine of x.
Yeah, and we're going to use theta. So cosine over sine. And what is cosecant? Yeah.
That's 1 over sine.
Yep. And when you divide those two fractions, what's going to happen? Yep.
You need cosine?
Yeah, the signs cancel because you would flip and multiply. The signs would cancel out. You'd be left with cosine in the top and 1 in the bottom. And the answer is just cosine. Now, if we had to do the next step, like some kind of calculus with that, it's a lot easier to do that with just a single trig function than it is with two trig functions. And they're exactly the same thing. Unsimplified, simplified. That's an easy one. That would be pretty straightforward. Any question on that? Because I'm just trying to give you an idea of the difficulty. That one's very straightforward. This one is also very straightforward. So let's change everything to sines and cosines. Okay. Let's start with cosecant. Okay. What's cosecant?
1 over cosine.
Not cosine. Careful. 1 over sine. So cosecant is 1 over sine times what's tangent? Yep. Sine over cosine. Okay, what's going to happen in those two fractions because you're multiplying? Yep.
Sine cancels.
Sine cancels. Because you're multiplying. If you made that a plus sign, which it's not, but if it was, you can't cancel sine in the top and the bottom. You cannot cancel across a plus or a minus sign. You can only cancel across a multiplication sign. So those do cancel. And you're left with 1 over cosine, which is what? Yep. Secant. So how do you know if you should leave it as 1 over cosine or secant? Well, I would argue if you can write it as not a fraction, that is simpler. So 1 over secant is simpler than saying 1 over cosine. Okay. Question on that? Okay. Still kind of an easy level idea. Now, there's two kinds of directions you'll see on these problems. Some of them say simplify. Some of them say verify. The difference between simplify and verify is simplify, they give you a problem, and you work with it until you think you're done. Verify is easier. Verify, they give you a problem. They tell you what it's going to simplify to. The goal is to take what's on one side and work with it till you turn it into the other side. So you know when you're done a verify problem, when you've taken the complicated side and made it simple. With a problem like simplify, sometimes you never really know when you're done. So simplify is a little bit more open-ended. The approach that we are always going to take when you have to verify something is to work with the more complicated side. It's always easier to take something that looks complicated and turn it into something simple. You don't want to try to take something that looks simple and make it look complicated. That's a lot harder to do. Because usually when you have something that's complicated, as you work through it, things start to cancel out. How would you reverse that? How would you know just what to put back in? You wouldn't. Okay, so that's why you always start with the complicated side and try to simplify it. You technically can work with both sides at the same time. We're not going to do that. Okay, we're just going to start with the complicated side and simplify. All right, so changing to sines and cosines. That's a good trick. It works a lot of the time. Okay, another trick is to rewrite things with a common denominator. So this only applies when you have fractions. If you don't have a problem with two fractions with different denominators, then this doesn't apply at all. And common denominator only applies to addition and subtraction problems. You never find common denominators when you're doing something like this. Just multiply straight across. Right, so let's try another one and see if this trick comes up. Okay, maybe it will, maybe it won't. So it's sine times cotangent plus tangent. A lot of the properties you already know with arithmetic also apply when you have just trig. So there's a property you're going to use on this one that you've used from algebra. Anyone have an idea what property is going to be used yet? Distributive. That's the first thing I would do. Is that the only way? No, there's other ways you could do it. But what comes to my mind is distribute out sine. So you have sine times cotangent plus sine times tangent. Okay, so now we've distributed. What do you think we could try now? We have two other tricks. Change everything to sines and cosines and write with a common denominator. Yep.
We just put them all over the same, like, we put them all over sine.
So let's pick one of the two tricks. You want to change everything to sines and cosines?
Yes.
Or you want to rewrite with a common denominator?
Rewrite a common denominator.
Okay. Do you have fractions with different denominators at this point?
No.
No. So we already have common denominators. You could think of these all as over 1. So let's change everything here to sines and cosines. How would I change the first one into sine or cosine? Yeah? I wouldn't do anything. It already is sine. What I am going to do is just put it over 1. Because we're going to be turning everything into fractions. So it's going to help to make that a fraction. How about cotangent?
Cosine over sine.
So it's cosine over sine. Sine, again, stays the same. And what about tangent? Yeah. Sine over cosine. Okay. What's going to happen there? Yeah.
For the first one, the sine cancels out.
Which ones cancel?
The first one, the sine cancels out.
Okay, so we have a sine in the top, sine in the bottom. How about cosine in the top, cosine in the bottom? Yeah?
That's not going to cancel out because that's on the opposite sides of the plus.
Yeah, I can't cancel across the plus sign.
It's not being multiplied. So we're going to have cosine plus sine squared over cosine.
Yes. So now we have cosine over 1 if you want, plus sine squared over cosine. All right. So we've used the trick of changing everything to sines and cosines. What's the other trick that I mentioned? Yep.
We need to figure it out so it's one over cosine, or like make it so it's a common denominator.
Right. We want to find a common denominator. So what's the common denominator between 1 and cosine? Yep.
It would be cosine.
Yes.
So we'd have
Cosine.
cosine squared, I'm pretty sure, up top, because we'd be multiplying it by cosine, and then on bottom there'd be cosine.
Yeah. So the way you find the common denominator, find a denominator, is multiply the two denominators together that you have. 1 times cosine is cosine. This denominator is a 1. We want to make it the same as that denominator. So multiply the bottom and top by cosine. What's cosine times cosine?
Cosine squared.
Cosine squared. Nothing changed in the second fraction. That's still sine squared. And the bottom is now all divided by cosine. So now we've used the trick of changing to sines and cosines. We found a common denominator. There's no other tricks. There's something there you have to recognize that simplifies. Yeah?
Is it one of the identities?
There is an identity in that problem, yes. Yeah?
One,
What's one?
the numerator?
The numerator. We said earlier sine squared plus cosine squared equals 1. That's exactly what you have in the numerator right now. You have cosine squared plus sine squared. So the entire numerator turns into 1.
Secant.
And 1 over cosine is secant. And that's your answer. So look at how complicated of a thing we started with. 3 different trig functions, distributive property, and we simplified the whole thing down to just secant. It takes a lot of practice to get really good at these. Yeah.
Would you still have like reached like the correct answer if you cross canceled cosine squared and cosine to make it cosine plus sine squared over 1?
If you did what?
Like, so cosine squared is cosine times cosine plus sine squared. So you cosine times cosine, you can cross one of those out for the denominator of cosine.
So you can't, like if you had something like 3 times 3 plus 4 times 4 divided by 3,
Yeah.
you cannot cancel a 3 there. There's no 3 that cancels. The only way you can cancel a number out when you have a fraction is like if you had 3 plus 12 divided by 3. Now you can cancel a 3 because you can do it here, here, and there. There's no 3 that you could cancel out of 4 times 4. That's 16. So if you're going to cancel a 3, you got to do it here, here, and here.
So you could have cosine plus sine squared over cosine if you did that. Then.
Well, that's what we had up here, cosine plus sine squared over cosine. So that'd be going back slightly.
Yeah.
Okay. Any other questions on how we got secant? Right. I'd say that's for what we're doing. It's not quite an easy one. It's not like really crazy hard, but it's definitely harder than the last 2. A little more going on. All right, let's try this one. So verify. So now we know what our goal is. We want to work with the more complicated side. Which side do you think looks more complicated, the right or the left? Yeah, the right. Yeah, no question. Right side is more complex. So we're going to keep manipulating the right-hand side until we turn it into sine somehow. So we know what to start with. We know what the goal is. How do we get there? So let me copy it down. So secant over tangent plus cotangent. Okay. So I have ideas of what we could try. What do you think? Yeah.
Let's start by converting all of them into the sine over cosine or 1 over sine or cosine and whatnot. Top.
So the top is going to be 1 over cosine, sine over cosine, cosine over sine. So we've changed everything into sines and cosines. It's not really a lot you can do with the top, right? The top is 1 over cosine. I mean, what are you going to do with that? Change it back to secant? I mean, there's not much we can do. But I think there is something we can do with the bottom. Anybody have a thought what we could do with the bottom?
They cancel out.
No, nothing cancels there. How come nothing cancels there? Yeah? That's addition. So like if you have 2/3 plus 3 halves, you can't just cross all that out because that one's flipped. If it was multiplication, you could say that yes, it's 1. But with addition, it's not 1. Any other thought what we could do with the bottom? Yeah.
You can multiply the left one by a sign and then multiply the right one by a sign.
Right. Exactly. So we're going to find a common denominator. And the way we're going to do it is multiply the top and bottom there by cosine. And the top and bottom there by sine. So the common denominator is going to be, I did that backwards, I'm sorry. Multiply the one on the left by sine over sine, and the one on the right by cosine over cosine. Sorry. So the common denominator is sine times cosine. It's the product of the two denominators that you have.
So, in the result of that, we have.
So there's the top. Top's just going to kind of hang out for a while, 1 over cosine.
We'd have at the bottom, when we combine everything, we'd have. We'd have 1 on the top of that thing at the bottom because
Right.
we would have sine squared.
This would be,
cosine squared.
This would be sine squared. This would be plus cosine squared. And that's what you would put right there. Well, what's sine squared plus cosine squared?
It would be 1.
1. Yep. So that's what the bottom turns into. Okay, so now when we divide two fractions, what do we do with the one in the bottom? Flip it and switch the sign. So we flip and multiply. So we have 1 over cosine times, what's going to go next to it? Yep.
Sine times cosine over 1.
Sine times cosine over 1. And now you are multiplying there.
Cosine cancels.
So the cosine cancels out. And what are you left with?
Sine.
You're left with just sine. Now you go back up and look and say, okay, is that what they said it should be? Yes, it is. So we simplified the right-hand side into sine. Maybe not the only way to do it, but we did it in changing sines to cosines, common denominator, flip and multiply and cancel. So that was like 4 steps. It's like 4 steps. Just to give you an idea, there might be some identities to try to solve that could be 30 or 40 steps. They get really challenging. But again, definitely harder than the first 2 we did. Any question on that? I'll show you another one. So changing sines and cosines, that's a good trick. Finding common denominator, that's a good trick. And the last general trick that I'm going to show you is multiplying by a conjugate. You know to use the conjugate, first of all, when you have a problem with a fraction, and you see something like a number plus a trig function, or a number minus a trig function. Conjugate. Number minus a trig function. Anytime I see something like that, right away I think conjugate. Okay, just trying to look at some other ones. Right, I'm not seeing a number plus a number plus a trig function, so I'm not thinking about conjugates here. Okay, yeah, definitely we could have some conjugates here. We have a number minus a trig function. Okay, I don't know for sure if it's going to be a conjugate, but it looks like that might be something I want to think about. Okay. Yes.
Is conjugate like the absolute value?
So conjugate is when you change the sign. So like if you had 1 plus tangent, the conjugate is 1 minus tangent.
Oh, so it's like the opposite of sine, of like the trig function.
So it's that, yeah.
For all 6 trig functions.
Yep, just like when we did imaginary numbers, like 4 plus 2i was a complex number, 4 minus 2i was the conjugate.
Yeah.
So, same idea. Except we're not doing imaginary numbers.
Yeah.
Yep. Okay. So that's really the last trick that I'm going to show you. Now we just apply them, okay, in different problems. All right, let's try this one. So it says cosine divided by 1 minus sine equals 1 plus sine over cosine. Is there a side here that looks more complicated? Like here, I think it was very clear. The right side is more complicated. There's no question. How about here? Yeah?
Seems like the left side's more complicated because there's just like one term. Are they the same?
I think they look pretty much the same. I mean, you've got, 1, 2, 3 things. This has 1 in the top, 2 terms in the bottom. Well, this has 3 things, but it's 2 in the top, 1 in the bottom. They're all sines and cosines. So I would say both sides look about the same. There's no clear side that looks more complicated to me. So the side that you start with is up to you. Do you want to start with the left side and try to change it to the right? Or start with the right and change it into the left? Yeah?
I think negatives are usually more complex than positives, so I think the left side would be best to do first.
Okay, so let's take the left-hand side. And we're going to try to change it into the right. Right, let's run through the different tricks that we know. Should we try changing this to sines and cosines? It already is. Should we try taking the 2 different fractions we have and making one denominator? Common denominator.
Is it possible?
Well, how many fractions do we have here? On the left-hand side.
We have 2 denominators. The one in the negative sign.
Those are 2 different fractions?
I mean, no, they're two different denominators. So, like, technically, you could do cosine over 1 plus cosine over negative sign. Can't you do that for the?
No, can't do that.
I mean, yeah, so only one fraction. Cosine over 1 minus.
We only have one denominator here. So if you don't have multiple denominators, you shouldn't be thinking about a common denominator because we don't have more than one. So the only trick that we have left is the one that I just showed you, which is to use the what? Yep. We're going to multiply by the conjugate. Yep. So you're going to take the conjugate of the bottom is 1 plus sine. Now, when you multiply by a conjugate, there's a kind of like a trick that I always use. Only multiply out what's in the bottom. Don't FOIL the top out. Because what's usually going to happen is something that's in the top is going to just disappear. If you FOIL it out, it's going to make it harder to do that. So leave the top exactly the way it is. If we need to do it out later, we'll do it later. But definitely FOIL the conjugates. And something good always happens. Okay, so let's FOIL it out. What's 1 times 1?
1.
So we get 1. And then 1 times sine.
Sine.
And 1 times negative sine.
Negative sine.
So those are gone. We had positive sine from the outer, negative sine from the inner. What's negative sine times positive sine?
Sine squared.
Negative sine squared.
Negative sine squared. Now that bottom is something. 1 minus sine squared. Let's go back. What did we say 1 minus sine squared is?
And identity. Cosine squared x.
It is cosine squared.
But it's still an identity.
Yeah, it's that first identity rearranged. So 1 minus sine squared can be changed to cosine squared. Okay, now let's do that and watch what happens. Okay, so top is cosine times 1 plus sine, and the bottom turned into what?
Cosine squared.
Cosine squared. Now, the top and the bottom have a common factor. It's kind of like having something like this. 3 times 1 plus x over 9. You can reduce. How many times does cosine go into cosine?
1.
1. And how many times, if you cancel a cosine from cosine squared, what are you left with?
2.
Cosine. So you can cancel 1 cosine from the top. That's gone. You can cancel 1 from the bottom. And look at what you're left with. 1 plus sine over cosine. 1 plus sine over cosine. So we turn the left-hand side into the right-hand side. Now, I wouldn't argue that we really did anything terrific. You change something that was this level of complexity to that level of complexity. It's really the same thing. Okay, it didn't really simplify a lot for us. But it showed us how to use the conjugate. That's why I did it. Okay. So any question on a conjugate one? My general advice is if you get stuck on an identity, it's probably better to just go to another one and try that one. Because if you get stuck on it for like 5 or 10 minutes, then you're probably missing something simple that you need to do. Because there's a simple way to do every identity I'm giving. There always is going to be a simple way to do that. Just look at what we got a bunch of them. Let's try one that I'm not sure how to do. Let's try this one. Okay, so we can choose which side we want to try to work with. Any thoughts? On which side we want to work with? You want to work with the left or the right? Yeah.
I think that the left is going to be more complicated, and that we're going to need to do some FOIL, or that we might need to do some FOIL since it's squared. So, well, not FOIL, but I think since it's squared, it's more complex, so I think the left will be more complex. And it also has a negative one, and like the other one just has, the complex thing about it would just be that it's minus cotangent x. And we would also check for identities, but I personally think the left one would be the most complicated.
Okay, so there are multiple ways to do this one. There's lots of different ways. What I'm going to show you, or what I'm going to tell you, basically comes from just, I guess, experience in looking at this problem. Okay, I'm looking at the top of this, and I'm comparing it to the top of that. Okay, and what I'm asking myself is, what could I do to this to make it look like that? Okay. So this position has a tangent. On the left-hand side, what's in that position?
Tangent squared.
A tangent squared. So what could I do to tangent to make it look exactly like tangent squared? Because that's the goal. I'm trying to make what's on one side look like the other. Yeah?
I mean, you could, what was it, the conjugate you said? So it gets the tangent squared. I don't see how else you get tangent squared.
Well, think of, I guess the same question would be, how could I make x look like x squared?
Get another like times x.
Times by x. So let's times that by tangent then. And then it'll look exactly like that. But if I times this by tangent, what else do I have to times by tangent?
Everything else.
Everything. I've got a times by tangent here, here, and here. And I'm going to hope that just by making what's in the top left look exactly like what's in the top left here, I'm going to magically hope other things just cancel out and it just works. Okay? So I'm going to try that and see what happens. Now, someone else might be saying, well, I'm going to start with the right-hand side and I'm going to change everything to sines and cosines. So, okay, you could try that, and maybe that would work even better. I think you're going to end up with lots of fractions. You know, sine over cosine minus cosine over sine. But then you could find common denominators. Maybe something would work with that. I guarantee something would work with it. Okay, but I'm trying to find the fastest way to do this. So I'm going to take the right-hand side, and we're going to just copy it down. And I'm going to try and make this look exactly like that. And I can already see by doing that, it's going to end up making this look exactly like that. So that's a good thing. So we said we're going to multiply everything by what?
Tangent.
Tangent. And that's a distributive property. So is that one of the tricks that I really mentioned to you? Multiply everything by tangent? No. I can't really write down every possible situation you could ever have. All right? This one's a little different. But you probably could do it with sines and cosines. I just think it's going to take longer. All right. What's tangent times tangent?
Tangent squared.
So tangent squared. And now think of cotangent. That's 1 over tangent. And you're multiplying it by tangent. So what's 1 over tangent times tangent?
Cancels. It's just one.
And we get just
Minus 1.
minus 1. That's perfect. It's exactly what we wanted in the top. Now, we just pray that that works in the bottom and something good happens.
The same will happen with the bottom, except it'll be a positive one.
Okay, so yeah, that's going to be tangent times tangent, which is tangent squared. And tangent times cotangent, yeah, we just did that in the top. That's positive 1. Now, if I can avoid it, I don't want to mess with the top anymore. The top is tangent squared minus 1 on the right. It's tangent squared minus 1 on the left. So that's good. So now, we just got to kind of look at this and see if we can figure something out with 1 plus tangent squared. Yeah?
It's already secant squared.
Right. The bottom is tangent squared plus 1. Go back to the formulas. Tangent squared plus 1 automatically turns into what?
Secant squared.
Secant squared. That just finished the whole problem for us. Yep. Okay, so let's go back here. Where was it? Nope. There we go. So 1 plus tangent squared, the bottom turns into secant squared. So the top, tangent squared minus 1. By a Pythagorean identity, the bottom turns into secant squared. And that is exactly what was on the left-hand side. So by multiplying by tangent, you were really able to do this problem in, well, if you count multiplying by tangent as 1 step, and then changing the Pythagorean identity, 2 steps. If you took the root of changing everything to sines and cosines, it might take you 10 steps. I don't know. I would have to try it and see. Yeah.
So also this is like technically like infinite solutions for the x, but will we ever need to solve for x in like something like this?
No, none of these are going to be solving for x. They're all going to be manipulating one side to look like the other.
But like in the future, will we ever need to like solve for x and like when there's like multiple trigonometric functions?
Yes.
Trigonometric functions in like
Yes, in 7.6. Yes. We'll be using the Pythagorean identities a lot when we do that section. Let's see if we have... I'm not interested in doing number 7. I'm just going to explain the point of it. Sometimes they ask you to prove something with, a left side and a right side, and they say prove if possible. So now that makes it even harder because now you're saying, well, maybe they're giving me something I can do. Maybe they're giving me a problem that I can't even do. If I want to figure out if something is even doable, what I will do is graph the left side in y1, graph the right side in y2. If they look totally different, then I know they've given me a problem I can't do. If they look the same, well, graphing doesn't prove they're the same. But if they look the same, then there's probably algebra I can do to prove they're the same. So that's kind of the point of example 7. The graphing calculator can kind of be used as a tool to figure out, should I even try to prove this is true? Right? That should be the easy part, deciding whether something is true or not. The hard part is proving it, doing all the steps. Yeah.
When you mean like look the same, do you mean like they like relatively look the same? Or
I mean like
overlap
exactly on top of each other.
Oh, okay.
So if I put the left side in y1 and it looked like that,
and then the other one overlaps,
and the right side looked like that, I would say, okay, they're probably the same thing.
Okay.
But if y1 looks like this and y2 looks like that, then I'd say, well, they don't even look the same, so I probably can't prove they're the same.
Also, when you said just because they look the same, it doesn't mean they are the same. Like,
Right.
What do you mean by that?
A graph is never a substitute for a proof.
Okay.
Just because one side looks like this and the other side looks like this, that doesn't prove anything. It suggests they're the same, but the only way to prove it is to go through the steps like that.
Okay.
So yeah, a graph is never a proof for anything. You cannot do that. All right, so let's try this one. It looks like somehow it simplifies to a fairly nice answer. Any suggestion what I might want to try first? Yeah.
On the left side has like 2 fractions, and it also has the -1 in the denominator, so I think it's going to be more complex.
Okay, yeah, I definitely agree. The left side is more complicated, so we want to work with that side. My question is, what do we want to try to do? Do we want to try to multiply the second fraction by a conjugate? Do we want to change to sines and cosines?
Well,
Do we want to think about a common denominator?
well, I don't know if this is practical or not, but maybe look for identities or things that are really close to being identities.
So, Rich, what were you going
I
to
was
say?
gonna say change it to all sine and cosines.
Okay, so 1 over tangent. What trig function is that when you flip the tangent?
Cotangent.
It's the cotangent. Well, cotangent is cosine over sine plus sine over cosine minus 1.
Then can we find like a common denominator?
We could try finding a common denominator and hopefully good things happen. So the common denominator is the product of the 2 that you have. Sine times cosine minus 1. What is this denominator missing to be the common denominator?
-1. Or cosine.
It's missing the entire cosine minus 1. So let's multiply it by cosine minus 1. What is this denominator missing?
Sine.
That's missing the sine. So let's multiply by sine. Okay, that's going to give me, what's cosine times cosine?
Cosine squared.
All right, that's good. I always like when there's a cosine squared, because then I'm going to hope for a sine squared, and then maybe I can do something. What's cosine times negative 1?
Negative cosine.
Negative cosine. Okay, we got a negative, and there's a negative in the final answer. Maybe that's good. Maybe. And what's sine times sine?
Sine
Sine
squared.
squared.
So sine squared. Okay, this is looking good, I think. We have a cosine squared and a sine squared. What's cosine squared plus sine squared?
1.
1. So that's 1. You still have negative cosine. And in the bottom, you have a sine times cosine minus 1. Is there anything in the top and the bottom that looks a little similar?
Cosine. And 1 minus.
Yeah, that 1 minus cosine, cosine minus 1. Let's leave the top the same. But let's factor a negative 1 out of this cosine x minus 1.
Negative sine times negative cosine plus 1.
So if you factor a negative 1 out, what does that become?
Negative cosine
It
x.
becomes negative cosine x. And what if you factor a negative 1 out plus 1? Now look at what happens. You have a negative cosine x plus 1 in the top. Negative cosine x plus 1 in the bottom. So there's nothing left in the top. So we got to just put a what?
1.
So you have 1 over negative sine.
So it would be negative cosecant.
Yep. Negative cosecant. And that's exactly what they said. So I think every problem we did today, we picked a pretty efficient way to do it. We didn't really get stuck on any of them, which is good. Okay, so not a ton of identities because some of them you could get stuck on. Okay, if you do get stuck, that's normal. But I will be after school today in case anybody wants to come by for extra help. Okay, and our test tomorrow will be on everything from this week. 7.2, 7.3, 7.4. I'll put a list of topics on the board on the video for you at lunch.
Nightmares from that.